Hi everyone, over the next few videos we're going to be looking at logarithmic functions. In this video we'll look at a basic logarithmic function, then we'll look at some transformations, then I'll give you an example. So what is a logarithmic function? Well, you won't be too surprised to find out that it's just basically y equals log base a x. Okay, now we're not going to worry about what base a is really. We'll assume it just follows the normal rules of it being a positive value not equal to 1. And we'll go from there. So y equals log base ax is the function. What does it look like? Well, let's do the same thing as we did in the previous videos when we were looking at exponential functions, and let's look at some critical points and see what they mean for our function. But I think maybe to make it a little bit easier to see what's going on, let's rewrite y equals log base ax into exponential form so we can sort of see where the a and the x fit in. So remember that if I rewrite that, I would get a to the power of x is equal, no that's not right, sorry. A to the power of y would be more intelligent, is equal to x, okay? So log base AC equals b, a to the power of b equals c, a to the power of b equals c, like so. All right, so let's start by looking at what happens when y equals 0. So when this value here, y is equal to 0, what's happening to x? So when y equals 0, this is a to the power of 0. A to the power of 0, doesn't matter what a is, a to the power of 0 is 1. Okay, so when y equals 0, a equals 1. So on our graph over here, if this is our y axis, struggling for words there, and this is our x-axis, then when y equals down to 0, then x is equal to, let's say it's there, 1. So let's pop a point in there. And we know that the logarithm function will be 1 at that point. Okay, it's a good start. Let's have a look at what happens when we take x on a bit of a journey to the right there. So when x is positive and above 1. So what's happening here? We've got, as x gets bigger and bigger and positive, so going along here, what's happening to the y value here? So as x gets bigger and bigger, what's happening to the y value? Well, it's going to get bigger and bigger as well, isn't it? You know, like as x grows, y has to grow as well. We can't go backwards. So as x grows, y must grow as well. But the growth is not the same as the exponential graph growth. What do I mean by that? Well, if I have a look at, say, let's look at the log. Let's assume it's log base 10. So if I have the log of 10, we know that's equal to 1. Okay, so when x equals 10, y equals 1. If I go just 1 unit along, when the log of 11 is 1.04, it's only a tiny bit more. If I go to the log of 50, which is quite a few units along, it's still only 1.69. And in fact, I don't get to 2 until I go to log of 100. Okay, so when x equals 1, y equals, so when x equals 10, y equals 1, and when x equals 100, y equals 2. So there's growth happening, but it's really slow. Looking at this one here, when x is 1, sorry, when x is 10, then let's just say a is equal to 10. That'll be 10 to the power of 1 equals 10. And then when x equals 11, 12, 13, 14, 10 to the power of just a tiny increase will get us to that number. So the growth, although it happens, is really slow. So from 1, the growth kind of looks like that. It's definitely growing, but it's growing slowly. Okay, well, what happens when x is a fraction then? Let's consider that for a second. When x is a fraction, y must be what? Negative? Because if I take a number, let's just say 10 again, and I'm going to end up with a fraction over here, let's say 1/10, what does y have to be for this equation to work? Well, y is equal to -1, just by the very definition of our exponents. Okay, so based upon this form of our equation, we can see that when x is a fraction, it can only occur when y is negative. Okay. In this form here, I guess what we're saying is that when I take the log of a fraction, the value of y is going to be negative. I mean, we can see that really quickly. If I go take the log of 0.5, you can see it's negative 0.301, and the reason why it's negative is for the logic I've just spelled out there. Okay, so we're going to get on the other side of the point there, this graph continuing down like so. Now, when is it going to cut through the y-axis? So let's think about that. When is it going to cut through the y-axis? It cuts through the y-axis when x is equal to 0. Now, I guess we need to work out what the log of 0 is, right? Log of 0. Log base a is 0. But again, if we think about it, if a is raised to any number whatsoever, the result is never 0, is it? Unless a is 0. So a to the power of 10 is a big number. A to the power of -10 is a small fraction. But there's no value of y for which I can get a value for x. Now, this isn't our function, this is our function. So to put it a different way, there is no value for x that will give me, sorry, I'll put it a different way. When I go for log of 0, I will not get a value for y. And we can see that from our calculations here. You know, I just get a random search result from Finder. I don't find a log of 0 because it doesn't exist. Okay, so it doesn't exist. So what does happen though? Well, as y gets more and more and more negative, so if y is a big, more and more negative, when y is a large negative number, then that means this number here is going to be a large negative number, which means, let's just say it's negative 1,000,000 and a is 10, negative 1, 2, 3, 1, 2, 3, 10 to the power of negative 1,000,000 is just going to be 1 over 10 to the power of positive 1,000,000. And that makes it a very small fraction. Okay, so what does that mean? That as y approaches negative infinity, x is approaching 0 but never gets to 0. So we end up with this kind of thing happening here, like so, with a vertical asymptote this time at x equals 0. Okay, vertical asymptote. So the function is only defined for values of x bigger than 0. It's not defined at x equals to 0, and as you can see here, I hope, is that it never crosses the y-axis, so it never enters these two quadrants. We can see that in Desmos if it sort of helps make it nice and clear. So there's y equals log base ax. I've just used a base of 2, I think. You can see that it starts creeping out here, and looks like it will cover every single value of y eventually, but it takes so long to get there. And as you can see, going downwards, it's approaching the y-axis but never actually crosses it, so it gets really close. So if I zoom up here, you can see it's just getting close. Zoomy zoom. Still getting close, but not ever reaching it. Okay. Similarly, if I zoom out, you can see that it keeps on increasing, but the further I increase it, the flatter it looks. It is still growing, but it's growing so slowly that you don't really see much of a difference in the height there. Okay, so that's basically the shape of the logarithmic graph. Now, I wonder whether you can see whether this logarithmic graph kind of looks familiar. Let me just zoom it back to home. You know, it kind of has similar properties, doesn't it, to the exponential graph. There's an asymptote, and there's some sort of growth curve there. So we've got something happening. Let me turn on the y equals a to the power of x graph. I'll just hide this for a second so we can see it. There we go. There's a beautiful symmetry there between the a to the power of x graph and the log base a x graph here. Okay, the symmetry of course is diagonal, and it kind of makes sense if you think about it, because y equals log base ax is actually an inverse of y equals a to the power of x. It's the opposite function, right? Because that's how it's defined. So it's not too surprising, I hope, that these graphs are very similar in shape, symmetrical. Now, you don't have to know about inverse functions this year, but it's probably just worth keeping that in mind, that when two functions are inverse, they are symmetrical when you graph them. Okay, so one last thing I will talk about and leave it there. So there's the basic form of the function. We will go and look at transformations in a subsequent lesson. But let's just talk about the domain and range of the basic function. So the basic function, and we've got that as being y equals log base a x, and then we've got the domain, and we've got the range. So the domain, I'll use that curly D for. The domain is equal to, well, what are the possible values of x? X is going to be real, but we have a limitation on x, don't we? In that x can't be equal to 0 and x can't be negative. Okay, I'll just turn off the exponential graph so you can see that. Okay, so x it's not defined over here. So we have x is a member of the real set, but x has to be greater than 0. Okay, sometimes you see this, by the way. You don't need to worry about this too much, but as written like this. So r with a plus next to it means all real numbers that are positive and therefore non-zero. For interval lovers, you can say the domain is equal to x, a member of 0, infinity. And again, make sure you do use round brackets for infinity. And because 0 is not included, we put a round bracket. What about the range? You might be tempted, especially if I zoom out, to say that the range of y is limited somehow, because we can see that it's not defined up here, but it actually is. It's just that you have to go a very long way to get that sort of increase happening. So the range is in fact all real numbers, because we're dealing with infinity here, which is difficult to put onto a laptop screen. But when x goes towards infinity, the value of y will, the possible values of y will cover all values between negative infinity. Oops, sorry, zooming in. Between negative infinity, because it keeps on going forever that way, and positive infinity. Fast growth here, slow growth here. Okay, so what's the range then? The range is equal to all possible values of y, such that y is a member of the real set. That's it. Or if you prefer, y is a member of the interval minus infinity to infinity. That's it for this lesson. Next video, we'll have a look at some of the transformations and we'll go from there. Thanks.